that helps us analyze everything from nearby asteroids to the edges of the observable universe. The idea of a telescope is straightforward: gather more light than the human eye can handle and magnify it. But the technology behind modern telescopes is anything but simple. There are multiple categories depending on the wavelength of interest, such as optical, radio, infrared, ultraviolet, X-ray, and gamma-ray telescopes. Each reveals a specific slice of the universe's story. Historically, Galileo's early telescope showed humans that Jupiter had moons and that Venus had phases, sparking the realization that Earth is not the universe's center. Centuries later, large ground-based telescopes like the Keck Observatory in Hawaii or the Very Large Telescope in Chile use mirrors that measure many meters across, collecting huge amounts of light. Earth-based telescopes, however, face problems like atmospheric distortion and light pollution. Adaptive optics can correct some of it, but many astronomers dreamt of telescopes in space, where the atmosphere wouldn't blur images or absorb key wavelengths. The Hubble Space Telescope, launched in 1990, revolutionized our entire view of cosmic history. By operating above Earth's atmosphere, Hubble captured some of the most iconic images in modern astronomy. Its deep-field observations showed thousands of galaxies in what once seemed like an empty patch of sky. Hubble also helped refine the Hubble constant, the rate of cosmic expansion, and mapped out star-forming regions in exquisite detail. Yet it mostly used optical and ultraviolet instruments, which only partially told the cosmic story. Infrared astronomy became crucial for looking deeper into the universe. Because of cosmic expansion, light from extremely distant objects gets stretched, redshifted, toward longer wavelengths. By shifting from ultraviolet and visible to infrared, older galaxies can ironically appear bright in the infrared region. The James Webb Space Telescope, JWST, therefore filled a pressing need. Its large segmented mirror, advanced infrared sensors, and position at the second Lagrange point, L2, make it sensitive enough to collect photons from objects formed a few 100 million years after the Big Bang, a time that was previously only faintly accessible. In practice, JWST stands out because it was specifically designed to probe the universe's earliest epochs. Its massive mirror, about 6.5 meters across, and unique cooling system allow it to detect faint infrared signals. The sun shield, composed of multiple layers, keeps the instruments extremely cold, preventing interference from the telescope's own heat. Once it arrived at L2, JWST underwent a complex unfolding sequence, aligning each mirror segment so that they functioned as one. Space fans worldwide watched with bated breath for the first images to come in, and they didn't disappoint. One particularly famous early release was JWST's Deep Field image, taken using its near-infrared camera, NIRCam. This snapshot unveiled thousands of galaxies, many so distant that their shapes were warped by gravitational lensing. Scientists saw arcs, swirls, and spots that might correspond to baby galaxies from the earliest billion years of cosmic history. For them, each little blob is a clue that either confirms or questions what we know about how matter coalesces into galaxies. Spectroscopic data from JWST's near-infrared spectrograph, NIR-SPEC, and mid-infrared instrument, MIRI, promise additional revelations about the chemical makeup, star formation rates, and velocities of these galaxies.